Hello, my name is Victor Rodriguez-Ortiz, and I'll be walking you through my solutions to the explicit method problem and to the one-dimensional problem from the book. Okay, so we're interested in using these one-dimensional transient explicit method equations to determine at what time the center of a brick wall will reach 425 Kelvin at certain boundary conditions. Okay, so let me walk you through my code right here. First things first, I had to import some packages I would use, such as NumPy and matplotlib. I defined some constants, such as the thermal diffusivity of our material, the brick wall. This dt value here is an arbitrarily chosen temperature interval. It's equal to half an hour, and I'll explain a bit more as to why I chose this number later. Dx here is my chosen length increment. Basically, I divided the length of the wall from the problem statement 0.5 by 8. It essentially sets the dimensions or the bins that I would use at each x-axis interval. So next is the boundary conditions. I just wanted to establish them so I didn't have to write the number each time, and so a bit more clear to see in the code. Of course, on the left side of a wall is 425 and the right side is 600 Kelvin. And here I want to explain some of the functions that I used in this code. So this first one, called tcalc right here, is because of the one-dimensional transient heat equations. Let me go back here and explain this equation right here. Right here at the bottom, I essentially wrote this as the function, and I separated them to two terms, this one and this one. And I know that if you choose your stability criteria correctly, you can actually cancel the second term, but I was interested in seeing how it would work out including this term, and it's not a difficult thing to add in. So term 1, as I said, was the first term of the equation. It's alpha times dt divided by dx squared plus t right plus t left. Go back to the equation. Alpha times dt over dx squared, times t on the right side plus t on the left side at the previous time interval. And so term 2 is going to be, term 2 in the equation, 1 minus 2 times alpha times dt divided by dx squared times the temperature at the previous time interval of that node. Then I just summed the terms up and told the function to return the output. I'll explain to you later how I used it. So these two pieces of code here are more just for functionality when I was writing the code. So this one here, this first one, set the width of any printed arrays. So since these arrays can get kind of long, and you'll see that, the end of the row might overlap with the beginning of that same row, so it just improved legibility by just having, if the row was or if the array was one row, just having that on one row, not multiple rows. So this next code here just helped enlarge the Jupyter IDE cell. So when I was working in it, some of the code would pass the screen. I couldn't read it without scrolling, and all it did was enlarge the working environment. So now we get into our actual calculations. And the first thing that I did was create a NumPy array, which is this AR initial array, with our starting conditions. So the left side of the wall is at 425 degrees Kelvin, or from our fear number from the variable I set. Then all the terms here are 300 because our wall is at uniform temperature 300 Kelvin at the beginning. And of course our t right, our boundary condition on the right side of the wall. And so if I go here, this is an Excel spreadsheet that I prepared, or a screenshot of one, just so that I can check my calculations as I go, and also kind of help visualize and set things up for the equation, for the problem solving. So this kind of row that I've highlighted is what we've just created in that AR initial here. And this dx value that I had previously mentioned This is where this kind of comes into play. So divided 0.5 into these intervals, and that determines the amount of columns in my array. Of course, if you divide it into more intervals, and then you would just get more columns in the middle here. So the next thing I did was define the second array, second NumPy array, and I essentially calculated, go back to this reference sheet, this second row. And I explained to you why I did this a certain way afterwards, but just bear with me. And so I said again, I set the first index to that boundary condition, same with the final index. But this time I used my function, which takes these inputs, takes the left input, which for the, if we're talking about this element here, which would be the, I guess the first element if you're using zero indexing, corresponds to this number here. And so according to this equation, you would need the left value at the previous time, the left value at the previous time, the right value at the previous time, and the value at that same node at the previous time, which are these values here. So it calls these values, inputs them into the function at t right. So going from left to middle to right, if you notice the function takes those inputs, t left, t middle, t right, all at the previous times, and it will return the output. So it will return the t at that node at the next time interval. And so I repeated that for every single, cell all the way down through in every column. And of course the final temperature value right before the boundary condition uses the boundary condition because it uses the left, the middle, and the right value. And so now all that was left to do was to stack these two arrays together. So at the end of the day, I would like to produce this entire, this entire array here. And so I took this first column that I created, I took the second column right under it, and I just stacked them together into one 2-row 8-column array. I'm using this function called vstack, or vertical stack. And this function is only takes one input, so you have to make sure to bracket the two arrays together, even though you're technically putting in two values. If you bracket them, it'll see it as one. So now I want to get into the while loop that I'll use to calculate the rest of the rows. So I'm referring to these values here, all the way down. Before we do that, of course, we have to initialize some variables so that we can eventually stop the while loop. And so I have this variable here, I equals 0, which is just a row counter, and you'll see how that works in a bit in just a second. T equals 0, which is going to count our time intervals, and this is going to be based on the arbitrary time selection or change in time selection I had done. And this is going to be a 1D list that contains all my time interval values. I did this because it would be simpler to just have Python make this list as it iterates through the while loop, and at the end of the day I'd have a full list that I could use to plot. So my x values, which would be time, eventually after this while loop I would have a time 0, 1800, 3600, and so on all the way down to 86,400. And so I would have a one row list that I could use for my plots very conveniently. So let's get into the while loop, and this will produce the rest of the array of the temperature profile. And so at each iteration of the while loop, it starts at t equals 0. So at each iteration of while loop, it will calculate it would add a value of 1800 or dt to the time. It would also iterate one row over, and you'll see why I place this in front of the calculations and not at the end. So this row here says that timeplot.append, and what that does, as I was mentioning previously, it adds the value of time to my time plot list, which is what I want to use to generate my x-axis for my plot. and it's divided by 3600 because time is in seconds, but I would need to report it in hours. So now we get into the nitty gritty. So I make this array, or designate this array 4, and I call it a numpy array. And you'll see the first term, as usual, is the boundary conditions. The second term, however, is a bit different. And so it's using my function, tcalc, and it's inputting for the first temperature left. It's inputting from the third, from array 3, a value of I comma 0. So row 1, because we iterated, we added 1 already to I, row 1 comma 0. So if we go back here, what that designates is this value here. Sorry, this one here. Row 1. So the second row in the array, remember that the array is now those two. So the second row in the array, because Python uses zero indexing, and the 0th column, which designate this. So that's our temperature to the left. Remember, we're trying to calculate this cell, this cell here. And so we need the 3 above values, these 3. And so it goes to AR3, it looks for the first, or the 1 index row and the 0th column. And that is the input it takes for TI left, all the way up here. And so you notice now we need TI right, and then TI middle, and then TI right. And so the next input that the function takes, tcalc, is the same row, right? So our row here, but it takes the first column, or the 1 index column, which would be the column right over. And so the next, and that's our T middle. And the next value that the function takes is, again, the same row, but the second column. And so that whole thing accounts for one value, which is this value here. And so, of course, we need to generate the rest of these values. And so I separated the array by commas to indicate, a new column every time, and just did the same thing where it goes from 0, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, and so on and so on. And if we look at the Excel file, it would essentially be 0, 1, 2, and then it would take this and slide it over 1, 2, 3, and keep calculating the value for the next row. So now we have this 2D array, AR3, and this 1D array, AR4. So what we need to do is add AR4 to AR3 so that next time we pass through the loop, it uses the value for AR4, because we need to use the values of the previous array. So just to repeat that here, this is AR3. This is AR4 we just calculated through one iteration of our loop, and now I want to combine them together to make an array like this. So the reason I couldn't start calculating, or the reason I had to start outside here with my arrays, is because if I wanted to use this method here and to create a new array and append the array, Python doesn't like when you try to call or reference a 1D array with more than one position. It would prefer that you just index. If it's 1D, it's implied that there's no other rows, and so I prefer you just put one value for index. But of course, to iterate, I have to be able to change my rows each time, and so I had to first generate a 2D array so that Python could recognize and say, okay, you can call the individual row and individual column. If I try to call the individual row and column on the 1D array, which would have to be our starting array from our givens, then Python would not let me. So that's why I had to start outside here, generate my first 2D array, and then I can start iterating and appending the new rows to the array. And so here's what I was talking about, appending the values. So I took AR3, which during the first iteration is 2 rows, 8 columns. I did the np.vstack and appended AR3 and AR4 together. And so AR4 gets appended as a row to the bottom of AR3. And now I have this array here. And so Python, the way the while loop works, it'll calculate the next row and then append the next row, calculate the next row, and then append the next row. So the matrix gets progressively bigger through calculations and as it travels through the while loop. So the limitation on this while loop, the reason why I chose 86,400 is because it's representative of 1 day in seconds. And the reason I had chosen dt to be 1800 in seconds is because it corresponds to half an hour. So I would get about 48 points in time. So after I exit this while loop and we have generated our full array here, this full array all the way down, I needed to do one thing to correct. So here in my while loop, the amount of t values and the amount of, I guess, rows of the array calculated are the same. It might be a little hard to follow. So essentially the amount of rows here in this array is the same as the amount of iterations on t and t values added to my time plot list. But when we step outside the while loop, since I had to do these corrections, you notice there's two extra rows in this array, right? Because it's a 2D array. And there's only one extra value here that's appended to time plot. So I end up with essentially one more row than I have time values. So if you could imagine that at the very bottom of this spreadsheet, this row here, there was an additional row under it, but there was no corresponding time. And so when you try to plot that, Python will return and say your x and y values for your plot are unequal. There's no corresponding data point for this final y point. And so what I needed to do is append an additional data point for my time values, which corresponds to 24.5, because it's at the end of the day. It's an extra half hour after the day. And this would allow me to plot the two values, because now my data sets are equal in the amount of elements they have. And so, of course, I don't want to plot that entire array. I just want to plot the values at the middle temperature values as they change with time. And so I need to subset my entire array. And so that's what this is. I created another array called mid-t val, or values. It's a numpy array. And the rows correspond to, it's a 1D array with all the values from AR3, which again, it's this full array. This is AR3 now after the while loop. And it takes all the rows, but only the fourth column. And so it takes all the rows all the way straight down, but only this fourth column here that's highlighted at the top, because that's our midpoint value. So now we end up with one time plot list, 1D list, and then one mid-t value array, again, 1D array. And so now we can go to plot, because our data points are equal and we have them all and they're all correct. And so I just changed I created a scatter plot here. Of course, on the x-axis, I want time plot. On the y-axis, I want my temperature values at the midpoint of the wall. And I changed some parameters here just to, I guess, tidy it up. I changed the marker to a dot because it's smaller than a circle and easier to read. The color to purple, because who doesn't like purple, or blue-violet. And I set the plot title, changing temperature with time, and the /n just denotes a new line, so it didn't extend too far over the entire chart. So the title is changing temperature with time for the midpoint of a brick wall. On my x-axis, I plotted time in hours, and I changed the ticks so that these ticks values here are the 0, 2, 4, 6, 8, so that it was easier to read. I did the same with the y-axis, where I labeled the temperature in Kelvin, edited the ticks so that they're easier to read, and I added a grid, again, just to improve legibility. And so from this plot here, I wanted to note that these black bars are not from my Python code. I just did it so that the answer for the actual problem is easier to read off. But Yeah, so here you can see that at a time, or the midpoint of the wall will reach a temperature of 425 Kelvin at a time of, looks to be 16.5 or close to 7 if we take that here as the midpoint. Okay, so let's move on to part C of the problem, or problem 1. And it was describing the stability criteria for this explicit method on 2D and 3D systems, because we were just worried about a 1D system previously. So for 2D and 3D systems, it's actually the same. And so we have this mesh Fourier number tau must be equal to less than or equal to 1 over 4. But where does this 1 over 4 value come from? Well, it's derived from this transient 2D heat transfer equation, the explicit method. And so in order for this term here, the temperature at the node in question, but at the previous time, because here I denotes time and I plus 1 denotes the future time. In order for this term to drop out, you would need tau to be equal to 1 over 4. If tau is greater than this value, then the equation blows up and you're not able to use this as a good way of solving the problem. And so another cool thing to note is if we take tau to be 1 over 4, this term drops out and we assume that there's no energy being generated or heat being generated at our point of interest. The temperature at our point of interest at a future time becomes just the arithmetic mean of all these temperatures. So T left, T right, T top, T bottom at the previous times divided by 4. Well, it's just the arithmetic mean. Okay. So here I just put this in case you're interested to look at the values. It was just a spreadsheet I used to check answers and help write the code. So let's move on to the second part of the assignment. This is a problem I chose in the book. It's P3-85. So chilled water enters a thin-shelled 5 centimeter diameter, 150 meter long pipe at 7 degrees Celsius at a rate of 0.98 kilograms per second and leaves at 8 degrees Celsius. The pipe is then exposed to ambient air at 30 degrees Celsius with a heat transfer coefficient of 9 watt per meter squared Kelvin. If the pipe is to be insulated with glass wool, insulation, thermal conductivity of 0.05 watt per meter Kelvin, in order to decrease the temperature rise of water to 0.25 degrees Celsius, determine the required thickness of insulation. So it gives us a situation of this pipe and then says we want to insulate it to minimize the temperature lost from the chilled water. And we want to determine the radius that's required for that insulation. And so here's the written part of my assignment. I feel like it's easier to, once you've seen the answer, it's easier to understand the code behind it. So this is a drawing of the pipe system. I drew the insulation here so I can get an idea. Water comes in, its insulation is glass wool, there's ambient temperature, length of pipe. So our goal, again, is to determine the needed radius of insulation for water temperature rise only by 0.25 degrees Celsius. And so my thought process was, so we were looking for the radius of insulation, and so we're going to be dealing with thermal resistances. You have to. And to calculate thermal resistances, we need a heat transfer. We need to know the heat transferred through our medium. So the first thing I calculated was the heat transfer rate using the m dot Cp delta T. This is relatively straightforward. The mass flow rate is given, the heat capacity of water is given or known, and the change in temperature is 1 degree Celsius initially at our first situation without any insulation. So that comes out to be about 4 kilowatts. So then I went to calculate the resistance in our cylinder, and I summed up all the resistance term. If you look at this diagram here, if the inside of the fluid and the outside is the air, and this is the pipe thickness, then between this point and this point here, we have convective thermal resistance for the fluid. We have a conduction thermal resistivity in the actual pipe wall itself, and then we have convective thermal resistance between the pipe and the fluid, which is air. And so if we sum up these terms, so resistance in the fluid, resistance in the pipe, and resistance due to the atmosphere, then we get our total resistance. And when we're interested in the insulation, and so the resistance. They're going to have an added resistance term eventually, and the resistance between our added insulation and our air fluid bound or our air insulation boundary is going to change. But what does not change is the convective resistance in the fluid and the conductive thermal resistance in the pipe. And so we can solve for these now and use them to plug into our equation later. And so I did. So this is thermal resistance in the fluid, thermal resistance in the pipe is equal to the total resistance minus our resistance between the air fluid or the atmosphere and the pipe. And so the total resistance is just going to be the difference in temperature between our surface and the difference in temperature between the surface and our average fluid temperature over our Q. And we can subtract that through our atmospheric resistance, which is 1 over our heat transfer coefficient times our surface area. So if we go down here, so our surface temperature is given to us as 30 degrees. And subtract that through our average temperature in the pipe. Well, if it's coming in at 7 degrees, exiting at 8, it has to be 7.5. And we divide that by our heat transfer rate, which we just calculated in watts. And so we subtract from that term 1 over our heat transfer coefficient of air, which is 9 watt per meter squared dot Kelvin, times the surface area of the pipe, which is just pi times d times L. D and L are provided. And that comes out to be 7.77 times 10 to the minus 4 Kelvin over watts. And so now that we've got this term, we can kind of look at the system of interest. We're interested in the insulation. And so we need to calculate a new Q because the temperature difference is supposed to be different. We only want it to change by 0.25 degrees Celsius. And so we do the same equation, m dot times Cp times delta T. So 0.98 times 4.184 times 0.25, and that gives us that the heat transfer rate, in order for water to only change by 0.25 degrees Celsius, has to be 1,025 watts. So we move on to the next page here. So we want to recalculate our total resistance with insulation now. This is what this image is here. You have the inside fluid in the pipe. There's some thermal resistance here. There's some thermal conductive resistance due to the pipe again. But now we have this added thermal resistance due to the glass wool on the outside of the pipe. And of course, we still have the thermal resistance between the atmosphere and now the glass wool. So our total, like I was just describing, resistance of fluid, resistance of pipe, resistance of the insulation, and resistance between atmosphere and insulation. And so we can input the equations for these values. And so our insulation comes out to this, so R2 minus R1 divided by the thermal conductivity in the insulation and the log mean surface area, plus 1 over, again, like we had said previously, the thermal conductivity of the atmosphere times our new surface area, because the surface area changes since we've added this layer of insulation. And so we do some simplifications here for this insulation thermal resistance term. So we write out our log mean temperature. We continue here and we can see that we can put the ln of A2 over A1 to the numerator and keep this A2 minus A1 on denominator. A2 minus A1 of course simplifies to 2 pi r squared L minus 2 pi r1 squared L. And so we can factor out 2 pi L, R2 and R1 now cancel. And so we're left with this equation here, where our new total thermal resistance is equal to the thermal resistance of the fluid plus thermal conductive resistance of the pipe plus natural log of D2, which is this diameter here from the center to the outside of the insulation, over D, our original diameter, divided by 2 pi KL, plus 1 over the heat transfer coefficient times pi D2L. And these two diameters being the same value. And so we can plug in some values, and the values we know. So of course the thermal resistance, the total thermal resistance is the outside surface temperature minus our average inside temperature of the fluid. Well, since we're going from 7 to 7.25 degrees Celsius, the average is 7.125. So we have 30 minus 7.125 divided by the Q we've just previously calculated, again based on that 0.25 degrees Celsius temperature difference. And this is equal to, like I said before, we would need this value later, thermal resistance of fluid plus thermal resistance of pipe. Here it is, 7.7 times 10 to the minus 4 Kelvin over watts, plus this term here, which is just a previous term with the values plugged in, the knowns plugged in, and this final term here, which again is this previous term with the values plugged in. And so it simplifies all the way down to this. So 0.02154 is equal to the ln of d2 divided by 0.05 divided by 47.12 plus 1 over 4,241.15 times d2. And so it's very difficult to actually solve this equation because the way you'd have to move it around and what the functions that d2 is enclosed in prevent that. And so use an Excel solver, you get a value of d2 is equal to 0.1263 meters, but we're not done yet because of course d2 is our new total diameter if you include our insulation. And so if you want to calculate the r sub insulation, or the radius of insulation, take d2 minus d, our original diameter. So essentially we're taking this diameter from this point to here minus the diameter of here to here, and we need to divide that by 2 because we want the radius. And so that boils down to about 3.82 centimeters as our radius of insulation. So now I want to go into how I try to tackle this problem in Python. So I need to import some of the necessary packages. So I imported SymPy, statistics, because I need the stat function, and math. So some of the constants that I had was the mass flow rate of the fluid, and my goal was same as the previous script, was to make it modular so you can tweak some values and still use it as long as the system is relatively similar. So mass flow rate of our fluid, which in our case is water in the pipe, specific heat of our fluid, again it's water, the heat transfer coefficient of our atmosphere, which is air, the temperature of the atmosphere, or really it's temperature at the surface of the pipe, the length of the pipe, L is equal to 150, the diameter of the pipe, 0.05, and our inlet and outlet temperatures. And I will change, you'll notice that these are the inlet and outlet temperatures from the first condition without insulation, but later in the code you'll see that I changed that. So beginning the code, first we want to calculate the amount of heat transferred in water, same as how we did manually, and I just multiplied by 1,000 to convert this to watts. Again, our mass flow rate times our specific heat times our temperature difference, which in the first case is going to be 1. And now we want to calculate the thermal resistance of the fluid, of course the convective thermal resistance, and the pipe, conductive, and I denoted the RFP for resistance fluid, resistance pipe together. So our R total is the surface temperature minus the average temperature of the fluid. And so I calculated this with the mean function from statistics package between T inside and T out. Of course, it's going to return, it's going to return a value of 7.5 because T in is 7, T out is 8. And we divide this by our Q that we just calculated. And that gave us our total thermal resistance of our system. And now we want to calculate the thermal resistance in the outside of the, or between the fluid outside and the pipe wall. So it's 1 over, like we had done in the manual calculations, 1 over the heat transfer coefficient times pi times d times L, where d and L are specified constants, which again you could change if you wanted to modify the problem. And this denotes our thermal resistance of the fluid plus the thermal resistance of the pipe. And so I just subtracted them because you need to find the difference between the two and set the variable. So now, just like we did in the manual calculations, we want to recalculate the amount of heat transfer, our Q value, in a situation where the temperature difference is 25 degrees Celsius. And so we redefine our outlet temperature to 7.25, and we recalculate using this Q equation as previously done. So T out is 7.25, T in is 7, and here's when I ran into some difficulty to explain in just a second. But now we have to calculate the diameter of insulation using thermal resistance terms. So like I did manually, our total is RF plus RP plus our insulation plus the R atmosphere and thermal resistance between atmosphere and insulation. And we just simplified the RF and our P values together so it can represent the actual variable I have written down here and here. And so I wrote the equations: R total, again, surface temperature minus our average temperature of the fluid divided by Q, R of insulation. And so here's where I ran into difficulties, because I wanted to use SymPy, which has a solver function, so you can put a variable into it and have it solve for you, like I had done in Excel, because it is very difficult to solve for the variable as is in the equation. And so I'd set the values of R insulation, or the equation for R insulation, and the equation for R ATM. And originally I tried to solve this way. That wasn't able to do it, and then I tried to set an equation called solve EQ, write up the whole equation, which is just what you're seeing here. R insulation is this, right? And R atmosphere is this, right? And of course we subtract R total, which is this value here. And so I tried many different functions, like solve, and I was having difficulties. I wasn't able to do it at the end of the day. This was the final one I tried to use, solve set, in which you plug in your equation, you tell the variable you want to solve it, and you give it a guess value at the beginning. The guess value is important because if you give it a log of 0, it'll throw an error, but it's still giving me some other errors. But the idea would be that from here, we would be able to get the value of de-insulation, and from there calculate the radius of insulation using the same method. So de-insulation minus the total diameter that we were provided divided by 2, and that will return to us, and print the radius of insulation, that will return to us the value calculated. Okay, thank you.